Thank you. Can you hear me okay? Okay, great. Thank you very much for coming. Thank you to the organizers. And I also just want to give a shout out to all my co-authors. I'm going to be talking about two papers today. The first one is called Constant Overhead Magic State Distillation. And the second one is called Quantum Codes with Addressable and Transversal Non-Clifford Gates. So hopefully by the end of the talk, I'll have been able to convince you that these are actually very closely related. The first one came out, I think, like August last year, and the second one came out like last week. So I kind of hurried this talk together, trying to get everything in. But I don't think any of my co-authors are able to be here, unfortunately. But Minshu is in Sydney, but couldn't come. Hayata's in Princeton. And my co-authors on the second paper are all back in Boston. But thank you to them nevertheless. So, okay. So the talk will kind of be split into two halves. So the first half will be about magic state distillation mostly. And the second half will be mostly about code construction. But again, hopefully I can convince you that there is a very natural link here. So first half, magic state distillation. And I want to start with like a lot of basic notions just to make 100% sure everyone's on the same page. So first thing to motivate magic state distillation is to explain what a transversal gate is. And a transversal gate is a way to compute fault tolerantly on encoded information in a code. So if your code has a very nice structure that you have given it, you've come up with a clever choice of code, then you can do a depth 1 physical circuit on the physical qubits, and that will allow you to execute a logical operation on the logical information. Now, these are very, very good things to do because it's a very low overhead way to compute fault tolerantly. Like, there's pretty much nothing more low overhead you can imagine than just doing a depth 1 physical operation. And so if we could do just transversal gates, we probably would. But we can't. There is a no-go theorem, very well-known no-go theorem called the Easton-Nil theorem, saying that there is no one code that can support a universal set of transversal gates. We have to do something else. And magic state distillation is a very natural construction to supplement transversal gates. And here, this is a very standard setup. It's very far from being the only setup, but a very standard setup is to do all the Clifford gates with transversal gates, and then to do magic state distillation to get you a non-Clifford gate. And this gets you universal fault-tolerant quantum computing. So what is MSD? So to say what MSD is, I should tell you what magic states are. And every gate considered in this talk will be a diagonal gate, so consider one. Consider a tau qubit diagonal gate, and suppose it's in exactly the third level of the Clifford hierarchy. So standard examples would be like the T gate on 1 qubit, or the CCZ gate on 3 qubits. And the magic state corresponding to the gate is just that gate acting on tau copies of the plus state. So given that U is a diagonal gate, what this is literally doing is just listing out the elements of U in a quantum state. So of course, T is a diagonal gate with 1 and e to the I pi by 4. The corresponding state is just 0 plus e to the I pi by 4, 1. CCZ is similar, so it's a superposition of the 8 computational basis states of 3 qubits, and the amplitudes are 1, 1, 1, 1, 1, 1, 1, minus 1. So why do we care? Well, we care because there is this thing called gate teleportation. And what gate teleportation does for us is it basically says that the gate and the corresponding state are equivalent resources as long as you're happy doing Clifford operations. So obviously, if you have the resource of the gate, you can get the state by acting on tau copies of the plus state. But what gate teleportation does is allows you to go the other way. You can consume 1 copy of U, and by doing some Clifford circuit, you can execute the gate U by consuming this ancilla on some other tau qubit state, possibly unknown to you. And so what this is telling us is that you can get universality with just Clifford operations and a supply of magic states. Because of course, all Cliffords plus a non-Clifford is universal. If you can do the non-Clifford by doing Cliffords with your magic states, then great. However, clearly so far nothing has been achieved. because I've just moved the problem of doing a fault-tolerant non-Clifford gate onto the problem of having a high-quality magic state, of having a magic state with a low error rate. And that is the problem that magic state distillation solves for us. So creating high-quality magic states is hard, but magic state distillation gives us a way to create high-quality magic states out of low-quality magic states, kind of as the name suggests. You can take in a large number of low-quality or high error rate magic states, and it will output for you a smaller number of higher quality or lower error rate magic states. And this will go via Cliffords only. So what this is basically telling us now is that Cliffords and a supply of low-quality magic states is universal, because we can do magic state distillation, use the Cliffords, turn these into high-quality magic states. We have the gate teleportation, so we can get the non-Clifford gate, combine it with the Cliffords, and we're in business. That's universal. Now, the kind of thinking is that magic state distillation is very expensive, and I think it is. It's very expensive. It is kind of a bottleneck in certain places. I'm also kind of hesitant to say magic state distillation is the bottleneck, because the landscape here is changing all the time. And we'll hear about some of these works here, but I think we can all agree it would be nice to do magic state distillation more efficiently, i.e. with a lower overhead. So what's meant by the overhead of a magic state distillation scheme? Well, roughly speaking, the overhead is the ratio between the number of noisy inputs and less noisy outputs. So you don't want to put in a billion noisy input states to get out one slightly less noisy output. So you want this ratio to be not too bad. And so a bit more precisely, the overhead is going to be a function, C of epsilon, where epsilon is the output error rate. So more precisely, it has overhead C of epsilon if for any small epsilon there is some large enough number of inputs n with some constant error rate, which can be converted into k magic states with error rate below that epsilon, where n over k is less than or equal to C of epsilon. So indeed, C of epsilon is basically the ratio between n, the number of inputs, and k, the number of outputs. And so C of epsilon is what we want to make smaller, although it's known that C of epsilon is really always going to take this form. It's always going to scale polylogarithmically in 1 over epsilon. And when I say in general this is true, what I mean is that every magic state distillation protocol ever discovered, the overhead has this functional form. And so the thing that we want to make smaller is that gamma. It's the degree of the polylogarithm, commonly called the overhead exponent of magic state distillation. And that gives me enough to state the main result of this first work, which is sort of given away by the title. So the main result is that we can get distillation now with gamma equals 0. So we can get asymptotically as efficient magic state distillation as you could ever even hope to do. Obviously, that's up to constant factors, as always. That still needs to be optimized, but up to constants, this is as efficient as you could ever even hope to do magic state distillation. And the paper is designed around doing this for qubits, but you can do this for any qubit of your choice. And this is, it justifies the name constant overhead, because obviously log to the 0 is a constant.
How big is the constant? Like, do you have a bound?
So
No.
So it's actually going to take further work to get an exact answer, although I will say that in some sense the paper should be called constant overhead, constant threshold distillation, because the two things you need to show to be constant are your overhead and your threshold. And like I can't say what the trade-off would be now, although I would say that if you're willing to take like a very small threshold, I think it's reasonable that the overhead could become like 1 in 20. For anything. So, and there will be like a universal number,
To have an order of magnitude.
Oh yeah. And then if you go the other way, if you allow a very high overhead, then your threshold might be able to get up to like, I don't know, 10, 20%, something like this. So thanks for the question. So in terms of the state that we're actually distilling, we want to do like a very well-known state, so we aim to do the CCZ state, so we can distill that with a constant overhead. where we actually have to put a bit more work into getting this well-known state. Yes, please.
Just a small question. So there's no dependence at all on epsilon, or like is there like some hidden dependence in a large enough n that depends on like...
Exactly, yes. So what's going on is in order to, the reason this is not completely crazy is because we're not creating something out of nothing. We have to take, in order to get lower error rates, we have to take a larger and larger number of inputs. That, I should say, is also true for all of the previous works. To get smaller error rate on the output, you have to take a large number of inputs. It's just that in the previous works, the number of inputs outruns the number of outputs, whereas here, the number of inputs and outputs both get larger, but they stay within a constant factor of each other. Thanks for the question. So yeah, no, so there's like pretty well-known conversions between all of the best-known magic states, like CCZ and T and really whatever else you want, and all these standard ones can be kind of converted up to constant factors, which aren't super important for this talk. So we can also distill T with a constant overhead. As for the main result that gets us there, it's the construction of the first quantum code to be asymptotically good and to support a non-Clifford transversal gate. And we're also able to get it to be explicit, which just means that we can actually write it down in a reasonable time. Again, just so we're all on the same page, let's just define these words. So asymptotically good. So the parameters of a quantum code are n, k, d. N is the number of physical qubits, k is the number of logical qubits, and d is the distance. And as n grows, the best that you can hope for with k and d is that they would grow linearly with n. If they both grow linearly with n, then you call your code asymptotically good, and it means that it has the best error correction parameters up to constant factors. Also, this is something to emphasize, because earlier I said that the meaning of a transversal gate is to act like with a depth 1 physical circuit, and that will do something interesting logically. And that's true as a very broad notion. But when I say here that a code supports a non-Clifford transversal gate, what I mean is there is some non-Clifford gate U such that acting with U to the n, so acting on all of the physical qubits, executes the logical gate U to the k. So it acts on all of the logical qubits. And I just emphasize this because I think like transversality is very well known for codes where there's one logical qubit, and it's very clear that you act on all the physical qubits, and this gives you the gate on the logical qubit. It's not so clear what we mean by a transversal gate when there's multiple logical qubits. But this has kind of become the standard notion of a transversal gate. Acts on all the physical qubits, and it acts on all the logical qubits. Okay, so with that, I can put this in a bit of context. So because magic state distillation is I guess, it's very central to quantum computing, in particular to fault-tolerant quantum computing, people have been trying to push the gamma value down for about 20 years now. So Bravy and Kitaev discovered magic state distillation in 2004, and they had gammas like 2.46. By the time you get to Bravy and Ha in 2012, they discovered gammas like 1.58. They actually conjectured that you couldn't push gamma below 1. They conjectured that sub-logarithmic overhead distillation is impossible. And subsequently in the same year, Coogee Jones came up with a protocol with gamma arbitrarily close to 1. It was not until 2017, with the work of Hastings and Ha, that they falsified that earlier conjecture, and they got gamma to be like 0.678. And prior to the present work, that was the smallest value of gamma for qubits known. I'll mention a qdit work that doesn't fit into the qubit table as we go along. But we'll be spending quite a lot of time with this paper from Bravy and Ha in 2012, and we'll kind of mention the relevance of this work, Hastings and Ha, 2017.
Sorry.
Yes?
I had a question on your previous slide.
Oh, yeah.
Can you talk a little bit about what you mean by constant overhead for the converting the CCZ state into the T state? Does that also account for any time overhead as well? And then my other question was, if you have this transversal non-Clifford gate U tensor K, how does your compilation work? Can you do that efficiently?
So the issue of space-time overhead is an important one. It's not something we consider here. We only consider the overhead of the states. And we do that because, like the table I just showed, all of those works just consider state overhead. The space-time overhead, there's still no known constant space-time overhead magic state distillation method. If you know the work from Chris Patterson and Quinn Yeung, I think it's called like constant space overhead, logarithmic time overhead, fault-tolerant quantum computation. It's like 120 pages. It came out a few months ago. They produce a low space-time overhead magic state distillation protocol, meaning that it has a constant space overhead, and I believe, and I hope I'm right, I believe the time overhead is like a polylog, where the degree of the polylog goes to 0. So the answer to your question is, we don't consider space-time overhead anywhere. In terms of the conversion, I think it's, can anyone correct me on this? Is it 2 T's gives you 1 CCZ? 3? Okay, 2 or 3.
I don't know.
It's a constant. So yeah, so it's a constant, which is great for the purpose of this talk. And then your other question was on compilation. What do you mean by that? Because what I'm saying is that acting on all the physical qubits just executes the logical u to the k.
I guess, like, in terms of, like, can you distill magic states that are addressable for different logical states?
You're talking about the second half of my talk. This is what I will talk about in about 20 minutes, yeah. So we'll come on to that, the addressability issue. So far, and thank you for motivating it so nicely. So this is very undirected. This is just a bit of a hammer, you know. And thanks for the questions. So this is kind of the history for qubit distillation. It would also be remiss of me not to mention these other 2 works that appeared like very shortly, like 2 or 3 days after we posted ours. One is from Louis Golowich and Venkat Guruswamy at Berkeley, and one is from Quinn Yeung at Harvard. And they had independent and simultaneous discoveries of the first quantum codes to support non-Clifford transversal gates and be asymptotically good. They didn't prove the constant overhead MSD. I will show in a second why having that gives you gamma arbitrarily close to 0 as an easy corollary. To get gamma equals 0, you have to work a bit harder. On the other hand, their code construction is actually nicer than ours. Our transversal gate is this big, ugly 10-qubit thing, and we have to distill that and convert the distillation of that to CCZ distillation. They get a code with a transversal CCZ gate with stronger methods, so that will also be important for the second half of the talk. So there's, these works are nice because they all kind of fill in different gaps. So in terms of the methods for the first part of the talk, I think my main job is to draw this connection between a quantum code with a non-Clifford transversal gate and a magic state distillation protocol. In particular, why, if that first code has better error correction parameters, does that give a magic state distillation protocol that is more efficient? And that's what I hope to explain in some detail. So first thing to say is if you have an NKD quantum code supporting a non-Clifford transversal gate, then you can make an MSD protocol with this overhead exponent. And this is kind of becoming known as the Bravey-Haar formula. Gamma equals log n over k over log d. And immediately you can see, and I'm going to show in detail where this comes from, but you can see if you have better error correction parameters, so if you have better k and d with respect to n, then you're going to get smaller gamma. Another thing is that if you had asymptotically good here, so if you had k scaling linearly with n, d scales linearly with n, then gamma is basically going to be 1 over log n, and then as you take n to infinity, you can get gamma arbitrarily close to 0. That's why these other 2 works, they get gamma arbitrarily close to 0 as an easy corollary. Clearly, you're not going to be able to get gamma equals 0 just from this formula. You have to do a bit more work. I won't go into that because it's kind of fiddly, but it is possible. I think I want to motivate this in full because I think this is the nicest way to connect non-Clifford transversal gates to MSD. So let's show how to build a magic state distillation protocol from such a code. Suppose we have an NKD quantum code and it supports a transversal T gate. Let's see how to distill the T state with an overhead exponent gamma equals log n over k over log d. And this all comes from Bravian-Haar's work in 2012. I think it's called magic state distillation with low overhead. Okay, and we'll be spending a lot of time with this paper. So consider the following subroutine. And this is a subroutine that we can use many times to get a full routine. So this subroutine is going to take in n low-quality t states, and it's going to spit out k higher-quality t states. And these n and k are the same n and k in the quantum code parameters. So step one, prepare k copies of the plus state and encode it into the quantum code. Now, this will all be Clifford. Obviously, encoding into a stabilizer code is always Clifford, so that's great. So k copies of the plus state in the code. Step two, use gate teleportation and consume the n noisy input states and use them to do a T-gate on each of the physical qubits of the code. We can consume the noisy input, we can do T on each physical qubit. So what we're doing is a noisy T to the n, physical. Now, we know that our code supports a transversal T-gate. The meaning of that is that T to the n acts in the same way as the logical T to the k. So clearly, if this were completely noiseless, doing T to the n would just give us logical T to the k, but the state that is in the code is the encoded plus to the k, so we're doing logical T to the k on logical plus to the k. That is just going to give us the logical state T to the k. But there are some errors on our input states. So clearly, we're not doing the perfect T to the n, and therefore, we're not doing the perfect logical T to the k either. So there's going to be some errors introduced, and we're going to end up with an errorful version of k copies of the T state encoded in the code. In an attempt to shave off these errors, we're going to try and suck ourselves back into the code space by measuring the stabilizers of the code. And at this stage, there will be some failure condition. If we measure a trivial syndrome, that is, we measure ourselves as being inside the code space, we measure no violated stabilizers, then we say this is a success. If we measure any violated stabilizer, any non-trivial syndrome, discard the state, give up, start again. But upon a success, we unencode from the code and we say, great, we have k copies of the T state, fantastic. And you can assume that it has a lower error rate. And in fact, I want to try and convince you that if the initial error rate was p of the inputs, then these outputs have an error rate that is something like p to the d, where the something like is again a constant. And now, why is this true? Well, if we got down to here, it means we succeeded. It means we didn't detect any error. So if an error did happen that's messed up our state, then it must be some bad logical error. But the definition of the distance d is the minimum weight of an error that will be undetectable and will mess up our state. But errors are happening at each location with probability p. Okay? So the probability of an error of weight at least d is something like p to the d, where the something like is just a combinatorial factor, like how many ways are there to make an error of weight at least d kind of thing. So indeed, initial error rate p, you get an output error rate something like p to the d. And then this whole subroutine can be concatenated with itself many times. So you take the outputs from one level, use them as the inputs to the next level, and keep pushing the error rate down and down and down. And that gives you a full MSD routine with, and you can do like a 4-line calculation and show that the overhead exponent of this thing is gamma equals log n over k over log d. And I hope I've convinced you that having a non-Clifford transversal gate on your code, if you have better error correction parameters, you can make a better MSD scheme. If k goes up, then you can distill more states at once, and if d goes up, then you can whack off more error in one go. So this was all from Bravian-Haar's paper in 2012. And so they formalized this notion of, non-Clifford transversal gate gives you an MSD scheme. They also gave us a unified framework for constructing codes supporting non-Clifford transversal gates, in particular supporting T-gates, at least up to Clifford corrections, which we don't care about. And they called this framework their triorthogonality framework. And they also want to spend a bit of time with this. So consider the following definition. Okay. Consider a binary matrix Consider a binary matrix. Suppose it has m rows, and the rows are of length n, i.e. the matrix is m by n. Okay? And we're going to call this matrix triorthogonal if the rows satisfy this polynomial equation. And this is a polynomial equation over the binary field. In words, what this says is we've got a binary matrix. Any distinct pair of rows has an even overlap with each other, and any distinct triple of rows has an even overlap with each other. Once I've got to there, I can just shuffle the rows around so that all of the rows which themselves have an odd weight are at the top. We'll just say they're the first k. And then all of the rows that have an even weight are at the bottom. We'll just say they're the bottom m minus k rows. So that's what this says. Again, I have a binary matrix. Any distinct pair of rows has an even overlap. Any distinct triple of rows has an even overlap. Okay? So far, we've got this weird definition of a matrix out of absolutely nowhere. There is then a matrix to quantum code construction that they give us. And it goes like this. Write the matrix this way. So we'll say the first k rows, which were the odd weight rows, call them G1. And then the last m minus k rows, the even weight rows, call them G0. There is then a quantum code corresponding to this matrix, which is called a binary triorthogonal quantum code. It's a CSS code, and you associate to the rows of G0 X stabilizers. And you put Z stabilizers on everything in the kernel of G. And that's the same as saying put Z stabilizers on any vector which has even overlap with every row of G. So clearly this is a well-defined CSS code because if the Z stabilizers are on everything with an even overlap of every row of G, the X stabilizers are associated with some of the rows of G. So clearly the Z and X stabilizers are going to commute. This is well-defined. But there was even more structure in the matrix G, and the triorthogonality of G gives us that this code supports a transversal T-gate, at least up to Clifford corrections. This is what Bravi and Haar showed. And so far, this probably feels quite ad hoc, like we've just come out of nowhere with a bunch of definitions, and it happens to give us a transversal T-gate up to Clifford's. It turns out this is the way to do transversal T-gates. This is not just sufficient, this is also necessary. This was actually shown later, but this should be considered as a very natural thing to do. This is not just sufficient, yes?
Is that assuming CSS code?
Oh. Okay, so they showed that, that's a great question. They showed that if you have a stabilizer code supporting a transversal T-gate, then they could build a CSS code with basically the same parameters supporting a transversal T-gate, and that it had to be of this form. This construction only gives you CSS code, so I couldn't say that it is the same for stabilizer codes. But yeah, as I say, given that you can make a stabilizer code with a T-gate into a CSS code with a T-gate, this should be considered as natural for all stabilizer codes. But yeah, how far you can do things differently with general stabilizer codes is a good question. Thanks for the question. So yeah, so this is it, you might be able to come up with codes that don't look like this, that support transversal T-gates. But it will always secretly be this. So Bravi and Haar, again, they gave us non-Clifford transversal gates, gives us MSD. They gave us a framework for constructing non-Clifford transversal gates on codes, which they called the triorthogonality framework. And people have used this, and it's gone really far. This is what a triorthogonal quantum code is. And in particular, Hastings and Haar used this exact thing to get gamma less than 1 for the first time. They got gamma being 0.678 in 2017, and they built triorthogonal matrices. And the way they built triorthogonal matrices was to take the generator matrix for a Reed-Muller code. And the reason this makes sense is because the code words of a Reed-Muller code are basically polynomials. And so if you write down a matrix whose rows are the code words of a Reed-Muller code, you're basically writing down a matrix whose rows are polynomials. And so I hope it's at least believable that those rows should satisfy certain polynomial equations like the ones on the previous slide. So yeah, what Hastings and Haar did, they said, let's build a triorthogonal matrix out of a Reed-Muller code. And the point is the algebraic structure of the Reed-Muller code gives us the triorthogonality. And that's how they got gamma down to 0.678. But that's where it stalls out. That's the limit that you can get with this framework, at least as far as we know. And to go and get smaller values of gamma, people have had to look at larger qubits. And the first time this was done was by Krishna and Tillich in 2018. They took Bravian-Haar's notion of triorthogonality for qubits, and they extended it to a notion of triorthogonality for larger qubits, in particular prime-dimensional qubits. They actually just had the same definition. So, take a matrix, except this time it will be over the field of p elements, fp, rather than just f2. And the exact same equations and the same matrix to quantum code construction gives them a quantum code. And again, they get a non-Clifford transversal gate. And this time, the non-Clifford transversal gate is this thing. So they've defined a notion of triorthogonality for larger qubits. They've done the matrix to quantum code thing. They've shown how to get non-Clifford transversal gates on larger qubits. And they also took inspiration from Hastings and Haar. Instead of using Reed-Muller codes, they used Reed-Solomon codes. The idea is the same. You have a code with algebraic properties. You should be able to write down its code words in a matrix, and those code words should satisfy certain polynomial equations. And using the Reed-Solomon codes, they were able to get codes on the larger qubits supporting this gate transversally. And they were able to get such good parameters that they became the first people to get gamma arbitrarily close to 0, although it came with one fairly significant drawback, which is that they could only get gamma arbitrarily close to 0 in the limit of infinitely large qubits. So in particular, they couldn't get gamma arbitrarily close to 0 for any fixed qubit. And to give you an idea of the numbers here, like in order to beat the Hastings-Haar value of 0.678, they had to take 97 dimensional qubits, okay? But it is super nice for the theory, and it was really inspiring for our work. One other thing to mention is that they're not distilling like a standard gate. They're distilling this U3. We'd like to distill something standard. We'd like to get gamma equals 0, and we'd like to do it on a fixed qubit. In particular, we'd like to do it on qubits. And in order to do that, the main conceptual shift that you have to make is to turn away from Reed-Muller codes, turn away from Reed-Solomon codes, and turn to algebraic geometry codes. And the reason that's an incredibly natural thing to do is that it's known from the classical coding literature that AG codes can do very much the same things for you as Reed-Muller codes and Reed-Solomon codes, but they can do it over a fixed field. Whereas for Reed-Solomon codes, the field has to grow to infinity, and that's what gives you the blowing up of the qubit dimension. For algebraic geometry codes, you can take a fixed field. And you also get the algebraic structure, and that's what's going to give us all of the non-Clifford transversal gate, triorthogonality stuff. The other big conceptual shift to make is you want a prime power. Whereas Krishna and Tillich had prime dimensional qubits, we now want to look at prime power qubits. So our route to constant overhead MSD for qubits will be to fix some prime power Q, let it be a power of 2 for reasons that will become clear momentarily. And then we define a notion of triorthogonality now for prime power qubits. Not qubits like Bravian-Haar had, not prime dimensional qubits like Krishna and Tillich had, but prime power dimensional qubits. And then we use the AG codes to instantiate this framework, and we develop a quantum code for Q-dimensional qubits supporting a non-Clifford transversal gate. Okay, so this is good. We can then get gamma equals 0 for Q-dimensional qubits, but we really want gamma equals 0 for qubits. The way that's done is a 2 to the t, and this is why I picked 2 to the t, a 2 to the t dimensional qubit is really the same thing as a set of t qubits. It's not just that their Hilbert spaces all have dimension 2 to the t, it's that, at least with a sensible choice, the Pauli groups are the same. The Clifford groups are the same. The Clifford hierarchies are the same. Okay? So we can convert this code on Q-dimensional qubits down to a code on qubits. And we can convert the distillation to the distillation of CCZ, as I'll explain in a second. But before I move on to that, this is the gate that we distill for the Q-dimensional qubits. So what's going on here? This is a diagonal gate. We denote the computational basis states of a Q-dimensional qubit via the corresponding elements of the finite field. As I say, it's diagonal, and it has entries on the diagonal plus and minus 1. They're e to the I pi something, and this something is in the binary field. It's either 0 or 1. Okay? And this something is a linear map of some polynomial. So this determines like the pattern of plus and minus 1s on the diagonal, and it just so happens that taking gamma to the 7 gives you a third level gate. The identity of the linear map's actually not important. It's the gamma to the 7 that takes you into the third level of the Clifford hierarchy. And so what's going on is we're building a code from AG codes for q-dimensional qubits. We're getting gamma equals 0 distillation of U7. We then qubitize that code. Every q-dimensional qubit, be it logical or physical, becomes a set of t qubits. And then we do this qubit to qubit conversion where U7 becomes a qubit gate. It becomes a t qubit gate. And because it's diagonal, it has plus and minus 1s on the diagonal, it's in the third level of the Clifford hierarchy. That on its own is enough to say that this thing can be decomposed, as a qubit gate, can be decomposed into a sequence of Z, CZ, and CCZ. Given that such a decomposition exists, that's actually enough for us because it's constant in size. You can always find it. But if you're interested, this is the decomposition. So U7 actually decomposes into 10 Z gates. Oh, I should say, this is T equals 10. This is our main construction. T equals 10, like 20-something CZs, and then 70 CCZ gates. And I just flashed this on the screen to show you how impractical this all is. But it exists. And then, as I said earlier, the other two papers, they don't prove the constant overhead, but they do have stronger conversions that allows you to completely avoid this. Yes?
How did you find that decomposition?
Matrix multiplication. So as I'll explain at the end, there's multiple ways to convert between a 2 to the t-dimensional qubit and a set of t qubits. And in order to do this most efficiently, you would want to minimize the number of CCZs in this decomposition. But the search space is actually too large for us to brute force. I can just pick one and just say, great, that one works. But if you wanted to do it most efficiently, then you would want a way to analytically look through all of the possible conversions. It turns out they correspond to bases for the field FQ over F2. That's kind of lists out all these conversions. And then once you do that, it's actually just matrix multiplication. Like if you, Z, CZ, CCZ, CCCCZ are all independent, and they span the gates with plus and minus 1 on the diagonal. And so you can write out their elements and do like a matrix multiplication to get this. Thanks.
I've missed a link in between 2 to the t and 7. Because gamma, you
Right.
take it in F2,
Mhm.
F2 is 2 to the t,
Mhm,
and 7.
7 is the power that we have to take to get into the third level of the Clifford hierarchy.
T, how much is t?
T is 10.
10.
So-
so t.
Yeah.
So is it always gamma 7?
Yeah, that's a good question. So it turns out this is in the third level of the Clifford hierarchy if t is greater than or equal to 3. We take t equals 10 for reasons given to us by the algebraic geometry construction.
Okay, that makes
Yeah, algebraic geometry is as you take a larger field, you can solve more equations.
The order of the root, something it's
Exactly.
you want a-
So yeah, the qubits are dimension 2 to the 10. The gate is U7. Thanks for the question. So yeah, these other papers have stronger conversions, and while they don't prove the constant overhead, they, instead of distilling U7 and then converting it to CCZ distillation with this mess, they can directly build codes with transversal CCZ. And those stronger qubit to qubit conversions are really important for us in the second half of the talk. So we'll talk about addressability now. So far, what we've done is we've built asymptotically good quantum codes with transversal non-Clifford gates, and this has allowed us to do magic state distillation extremely efficiently as you could ever hope to do it, at least in the asymptotic regime. However, this relation, u to the n is the logical u to the k, is not useful outside of magic state distillation. If you want to do general computation, it's not helpful to be hitting every logical qubit with the same gate at the same time. You would like to be able to talk to your logical qubits in particular. You would like to be able to address them. I mean, you can ask yourself, how many algorithms can you think of where it's useful to hit every qubit with the same gate at the same time? And you might say, well, maybe there's some with the Hadamard gate and things like this. But really, I think you'll agree, we want to address particular qubits. So we want a much stronger condition now on our codes. We want to be able to transversely address particular logical qubits. So now we don't just want u to the n is the logical u to the k. We want, given any particular logical qubit, we want to be able to act with a different transversal operation on the physical qubits to talk to that particular logical qubit. And we want to be doing this with non-Clifford gates. Yes?
Oh, yeah, I have a question. Yeah, so the way I usually hear magic state distillation being talked about is you have like a magic state factory, right? Or like it's just producing like a bunch of states. And presumably the code that you use to like do this distillation would not necessarily be the code that you use to do like in your actual computer to do like all your logic, because presumably, I mean, provably you can't have like efficient differs on one and transversal. Yeah, you know what I mean.
I do know what you mean.
Yeah, so like, okay, so I guess my point is like you would anyway have to use two different codes, right? Where for one you kind of want to maximize the number of magic states that you would like, so that then you send them to the other code. So what would be like the application that you would see for like addressability?
It's a good question. So essentially what I'm going to say in a moment is that there have been no codes at all for any application designed so far with transversally addressable non-Clifford gates. So no matter the application you want, this can fill it in. I mean, and if you want an application, you'd have to fit it into a whole fault tolerance protocol. But I mean, if you can, for example, address things with CCZ, maybe, I don't know, code switch and then do a bunch of H's, or if you can address things and then, inject magic states into that code, things like this. The point is that, we're going to present codes with properties that have never been discovered before. So we don't have like a fault tolerance scheme in mind to use them in, but that's further work. Thanks for the question. So we want codes, we want good parameters, we want to be able to transversely address particular logical qubits, which means that we act in a transversal way on the physical qubits. That lets us address logical qubits, and we want to do it with non-Clifford gates. But before I tell you our results, let me just give you the context, like what's known about addressability thus far. First thing to say is that if your code has one logical qubit, addressability is just not a thing. This is one good reason why the logic on the surface code is so well understood, is there's only one logical qubit, and so you can just act on it. A similar comment holds for the color codes. But if we want to reduce the eye-watering overhead of quantum error correction, then one good thing to do would be to scale to high-rate codes, but then addressability becomes an issue. Talking to particular logical qubits becomes an issue. And many people just avoid this issue. If you look at a lot of fault tolerance proposals, they will say, just act on the whole space. And they will also often say, it would be really nice if we could act on particular logical qubits. There are ways to act on particular logical qubits, but they're not transversal. People have looked at peaceable fault tolerance. There's also code surgery. And it is definitely worth saying that the overhead of these techniques is coming down, and they're also agnostic to the code. So these are really powerful things. On the other hand, it doesn't matter how much you improve these things, they will always be higher overhead than transversal gates. You're not going to get something lower overhead than acting with a depth 1 physical circuit. So it would be really nice to be able to do things transversely, i.e. act transversely on the physical qubits, address the logical qubits, and we want to do it with non-Clifford gates. I will mention that there's a couple of works with transversely addressable Clifford gates. As far as we're aware, this is the first with transversely addressable non-Clifford gates. There's also this folklore intuition that some people might have heard of. there's this intuition that says that if you have a transversal gate in the Lth level of the Clifford hierarchy, then you get a transversally addressable gate in the L-1th level of the Clifford hierarchy. And the way this goes is, if you have this transversal gate, then conjugate a logical Pauli by your transversal gate, and then depending which logical qubits you act with the Pauli on, that will give you the addressed gate on those logical qubits. And I don't want to spend too much time on this, but essentially I just want to say this folklore that's going around is not true for multi-qubit gates. It is true for single qubit gates, but we have nothing to instantiate it with because all of our constructions are multi-qubit, but it's not true for multi-qubit gates. And I'm a little short on time, so I'll say why it's not true in the case of CCCZ and CCZ briefly. But the intuition would tell you, if I have a transversal CCCZ, I should have a transversally addressable CCZ. And I'll show you why that's not true. The notion of a transversal CCCZ gate says that if I take 4 code blocks, and I act on physical qubits 1, 2, 3 with CCCZ, so physical qubits 1, 1, 1, 1, 2, 2, 2, 2, and so on, that will execute the logical CCCZ across the 4 code blocks on logical qubits 1, 1, 1, 1, 2, 2, 2, 2, and so on. That's the meaning of transversal CCCZ. What the folklore intuition that I'm referring to then calls for us to do is to conjugate a Pauli, there's also a Pauli at the end, but conjugate a Pauli via this transversal gate. And based on which logical qubit I act on, I should be able to address that logical qubit or that sequence of logical qubits with CCZ. And indeed, that's true. I can transversally address CCZ. But the point is that I'm only able to address the operators AAA. So the only things I can address are logical qubits 2, 2, 2 across 3 code blocks, or 5, 5, 5. I can only do these operators. This is still not strong enough to be computationally useful. It's a small step above the u to the n equals u to the k thing, which was hitting everything. But this is only allowing me to hit logical qubits with the same addresses in 3 different code blocks. This, in particular, you couldn't just beyond a constant size set. So it would be classically simulatable. So with that out the way, I can state the results. So we construct the first quantum codes to support transversal addressable non-Clifford gates. We get such codes with nearly asymptotically good parameters. Whereas in the first part of the talk, they were asymptotically good. Here, they're only asymptotically good up to a polylog, so we lose a polylog. But the addressability is pretty much the strongest notion of addressability you could think of. Given any triple, so not just AAA, given any triple of logical qubits, possibly in the same code block, or possibly across 3 code blocks, or 2 in the same, 1 in a different one, you can address those 3 logical qubits with the logical CCZ via a depth 1 circuit of physical CCZ. And this result is obtained, I've mentioned Reed-Solomon codes before, for very similar reasons why they were useful in the first part of the talk. They're useful here. They have nice algebraic structure. So we do this using particular properties of Reed-Solomon codes. We would also like to understand the transversal addressability from a higher level. And to do that, we develop a general framework for constructing codes with transversally addressable gates. And this encompasses all of the frameworks that we've talked about today, all of the relevant frameworks in the area. So we have this framework, and it can encompass the original Bravihar triorthogonality notion. It can encompass the Krishna and Tillish one for prime dimensional qubits. It can encompass our one for prime power qubits. And it can also extend these notions to build codes with addressable transversal gates. To give you an example of some of the things this can do, it's more general, so it's more agnostic to the input, but its results are weaker than what I had on the last slide. So for example, you can get asymptotically good codes, so better parameters than the last slide, but you can only do CCZ on pre-designed, non-overlapping triples. That's still stronger than the folklore intuition because they're in the same code block. And then, just to show the flexibility of our framework, I should say we call our framework addressable orthogonality. the flexibility is best shown by saying we can also deal with T-gates. We call this bit addressable triorthogonality. And you can get transversal and addressable T-gates up to Clifford corrections. So this is like a direct extension of Bravey and Haar's original triorthogonality framework. As for how this is done, I'll go quickly over this. As I said earlier, it was the algebraic structure that's giving us transversality. Basically here, we need even more algebraic structure to get transversal addressability. So these were the equations I showed earlier, and that gave transversality of a T-gate. If the rows of your matrix instead satisfy this higher degree polynomial, then you get transversal addressability of the T-gate. And we show that all the codes mentioned, like Reed-Solomon, algebraic geometry, have enough structure to satisfy these requirements. So in the last few minutes, I just want to summarize and go over some open problems, because there's so many open problems that this gives us. So on the first part, constant overhead MSD, it's theoretical, it's fine for the theory, but you should not try and build this ever. Of course, if you had an infinitely large quantum computer, this would be the way to do magic state distillation. Nothing could ever beat this. But the code, the size at which this becomes useful could be completely impractical. And indeed, I believe that to be the case for the algebraic geometry constructions, which give gamma equals 0. On the other hand, I do think that there are some ideas in these papers that could be of practical utility. So the Reed-Solomon-based constructions have not been properly worked out, and you could combine the Reed-Solomon constructions and the qubit to qubit conversions and try and put these together and work out how well these can do MSD at reasonable lengths. And this is sort of promising, and we're working it out now-ish. And so this might end up giving us some actually practical, very efficient MSD schemes. In the asymptotic regime, this comes back to your question earlier on the actual constant. What is the actual constant that we can achieve? You'd also have to balance that. What is the threshold you can achieve? What is the overhead you can achieve? What are these actual constants? And then just to give you some remaining open problems, something we talked about earlier was the different conversions. These conversions are not fully understood in the practical regime. Converting a 2 to the t-dimensional qubit down to qubits, not fully understood, especially at small lengths. So we'd like to do this more efficiently. LDPC codes with non-Clifford transversal gates. This is a massive thing that many people are working very hard on, and nothing I've mentioned in this talk has been LDPC. So, it's either restricted to MSD or just theory, probably. But as I say, these are new properties for any code, LDPC or otherwise. The first steps are being taken towards having non-Clifford transversal gates on LDPC codes, and I've listed some of them here. But this is going to be hard ongoing work, probably for a year or several. Another open question: what is the upper bound on the constants from the last slide? On the last slide, I was saying, what is the achievability of the overhead in MSD? But what would be the best you could ever hope to do? And then if you establish such an upper bound, could you, get the lower and upper bound as close to each other as possible? I think this is interesting for resource theories. Also, I mentioned earlier that it was known that Bravey and Haar's triorthogonality framework was not just sufficient, but also necessary for getting a T-gate. We actually don't know similar necessity statements beyond the T-gate, and it would be really helpful to have these to direct our attention. So it would be nice to go beyond the T-gate and figure out what are the necessary and sufficient conditions for a code to have them. And then finally, it's kind of an obvious one, but the main result of the second work was asymptotically good up to polylogs, and it had a fully addressable CCZ. Can we get that asymptotically good, maybe using particular algebraic geometry constructions? Thank you very much for your attention. Yes.
Hi, thanks, Tom. This may be more of a comment. I want to. You're saying if you can only do
Yeah, I should maybe caveat what I say and say it depends what else you combine it with. This comes down to the issue that we talked about, which was like, what are you going to do with these codes? Like, what fault tolerant scheme? These are just codes. To put these into a whole fault tolerant scheme is further work. I mean, you are right that it does, I suppose, enable you to simulate certain things. But I think, yeah, you want to be able to generate entanglement across lots of stuff. But yeah, no, you are right. If your entanglement is across constant size sets, then you can simulate.
Hi, awesome talk. I have a couple questions, but I'll try to just. I suppose the question I'm going to ask is also something that you kind of said don't believe is true. But do you have some notions for like how the finite n scaling is for these kind of schemes? Because
Oh, yeah, for that.
This constant overhead is kind of assuming you can take sort of n.
Right.
Right?
Yeah. So you're asking, so how, like, what sort of numbers does the constant overhead? I think the best way to answer that, because it's somehow hard to characterize this because it scales, but probably the best way to answer that is to say, like, what is the smallest n that would give us gamma less than 1? Because rather comedically, the first time gamma was made less than 1 by Hastings and Haar, they did it on 2 to the power of 58 qubits. And that's not practical, I don't think. So, you know, how can we get gamma less than 1? I believe we can do it on maybe like 50,000 qubits, somewhere around there, like somewhere between 10 to the 4 and 10 to the 5. Yeah, I think the Reed-Solomon could do much better. Like, this is, as I say, what we're working out, and we're actually trying to get practical MSD with Reed-Solomon codes, and it's believable that you could get gamma less than 1 on like low hundreds of qubits.
I have a second question. I'm trying not to ask questions about things you spoke about in the talk specifically, but is it true that this sort of linear error correction decoding radius is kind of central to getting this constant overhead and being able to do your error correction?
Indeed, yes. Yeah, so that's how we go from the gamma to 0 to the gamma equals 0, is that we do the Bravian-Haar framework that I showed you, and then instead of doing the post-selection, we do error correction. And you know, we also show that you can do this error correction decoding problem efficiently. And yeah, you are right that actually getting the constant overhead, that's done by being able to decode up to, you know, linear fraction of the distance, a constant fraction of the distance, which is itself a constant fraction of the block length. So yeah, it is absolutely central to getting a constant threshold. Yes.
Eddie, did you have a question?
Uh-oh.
Yeah. I have a question. Oh, sorry. No, sorry.
Yeah, I have, so like regarding the addressability, I was curious about a detail. So like, I understand that with addressability, you can pick the gate and then your construction would give that transversal instantiation of that gate on the code. Is that composable in the sense of like, can I pick 2 gates that like, if I were to act with them, they would act on like separate, like unencoded qubits. If given that guarantee, can I still get an encoded composed gate that still acts transversally?
Yeah.
Does that make sense?
It does, and if I think I'm understanding you correctly, this is actually one of the open problems written in the paper.
Okay.
So the way I'm understanding your question is like, you know, what we can do is we can pick out any triple, and we can do a depth 1 physical circuit to do the logical CCZ on that triple. What about groups? What about groups of triples, and can you do those with a depth 1 circuit? The answer is our construction actually allows some groups. And like maybe if you had a particular circuit, then you would want to compile things so that the CCZs you're doing all sit in a nice way so that you can do it all via depth 1 circuit. The question is, can you do any group? Can you do like any group of logical triples via a depth 1 circuit? And this also it might be possible to exclude this with a no-go theorem, because you're asking for so many logically distinguishable operations on your code space, and there's only so many depth 1 circuits. So you know, you're asking for exponentially many operations, so it might be possible to exclude this.
Well, we've sort of hit 12, so maybe take any remaining questions offline. So let's thank Adam.